Hello everyone, welcome to my introductory series to computer architecture. Um, I'm recording this at home, so the microphone quality will likely be quite a bit worse, as well as just the overall editing quality, so I apologize for that. But I hope you can find this video helpful for your computer engineering or software engineering or electrical engineering journey, whenever or if ever, or if you just want to learn something new. This is part of my fundamentals series where I'll go over some of the basics like logic gates, as well as some basic VHDL programming strategies that you might find of interest. So, getting into logic gates are the basic building blocks of computers. You can think of them effectively as a slight abstraction of transistors to obtain a certain behavior. You'll see these behaviors later, but if you've programmed before, you might know when you do like an if statement, you do if variable x is true and if variable y is true. That and operator is Boolean algebra, Boolean logic. Logic gates are an abstraction of transistors to obtain that Boolean like behavior. So let's go ahead and hop into the first logic gate here. And the first one that we'll talk about is the AND gate. I apologize for the low quality image. I thought it was an SVG, but unfortunately it isn't. But bear with me. An AND gate um, will take in two or more inputs, and if they're both true, the output Q will be true. You can see the symbol on the left. You have A and B as your inputs and Q as your output. On the right, you see the truth table. You see A, B, and then A and B. A and B is functionally equivalent to Q in our schematic. That up arrow symbol is the Boolean algebra and symbol. And you can see this is a truth table, and you can see if they're both false, the output is false. And if one of them are false, the output is false again. And only once all the inputs are true is the output true. This is a very helpful logic gate. It's kind of like a foundational one. Most people learn this as their first gate, so I hope that makes sense. The next gate is the OR gate. You take in one or more or two or more inputs again, and if either of them are true, the output is true. So as you can see, it has a different symbol here. It has a curved back end and then a more pointier front end. Um, that's just the symbol that's commonly used. You can see in the truth table, A and B, it has the same pattern. You have false, 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 true, true, false, true, true. And then you can see on the output, this is the downwards arrow, this is the OR symbol. When they're both false, it's false, otherwise it is true. Next we have the XOR gate. This one's quite a bit more complicated. It's similar to the OR gate in terms of a symbol, but it has an extra line here on the back end. The difference for an XOR gate is that it has two inputs, and if they're both true or both false, the output is false. So basically, one or the other has to be true, otherwise it is false. And you can see that in the truth table here, that when A is false but B is true, it is true, and then when A is true and B is false, the output is true. The Boolean symbol for this is the plus with the circle around it, or a circle with the plus inside of it, depending on how you look at it. Um, the XOR gate has a lot more functionalities than you might initially expect, and you'll see that later, especially with it can functionally be used to determine if an input is the same or not. And then the last gate that we'll cover here that's a specific gate is the NOT gate. The NOT gate is right now you can see it's a triangle with the circle on the end. This circle on the end actually denotes if a gate is a NOT gate or is inverted. You can think of this as an inverter. If it takes in false, it outputs true. You can see this little like dash with the bottom line on the right. That denotes that is not. If the input is false, the output is true, and vice versa. This is actually a much more helpful gate than you might initially anticipate. And the NOT functionality, the inversion functionality, can be applied to multiple gates. So this is you can apply the inversion to any gate by denoting the circle at the end, or circles on the input to devote to show that they're being inverted. But for an example here, this is a NAND gate, a not AND gate. It's an inverted AND gate. And you can see that the output is always true unless it is false. I picked the not NAND gate because, uh, again, you first learn the AND gate in this series as well. And you can build any other logic gate using the NAND gate. We won't get into that in this short video, but you can effectively chain these together in different ways, and you can achieve the same output as any other gate that we have previously covered. I hope you enjoyed this short video. I apologize for the poor quality, but I hope it can be of use for you, especially if maybe you're reviewing if you're getting into a computer architecture class, or if you're studying your digital logic courses. So good luck and have fun.